Okay, so we'll start. Okay, so good morning. Welcome back to Chemistry 580 and Physics 580 after a spring break. I hope you had a nice one. Did you enjoy your spring break? Did you have time to enjoy it? Yeah, I know. You just did more research.
That's right.
Okay, but that's what we like doing, so I guess it was all good for all of us. Okay, in any case, today I hope we'll start talking about the independent particle model approximations. Approximations where we use a single slater determinant to represent a Many-Fermion state or Many-Fermion system. Those are all these approximations that are behind various types of mean field theories. Okay, and in particular I'd like to discuss the Thouless theorem. It's a very beautiful theorem, very helpful in all these considerations. But before I get there, let me remind you where we are. So we are now in our material at the point where we discussed very thoroughly, I believe, the rules that apply to diagrammatic calculations. In particular, we dedicated the last lecture to calculations based on the Hugenholtz diagrams. Okay, as you remember, we developed the rules, and we actually developed a very efficient procedure which starts with the non-oriented Hugenholtz skeletons, and we assemble the oriented Hugenholtz diagrams or skeletons, then you throw indices in them, okay, and then you evaluate these diagrams with the help of Brandau diagrams, which we need to consider to get the information about the sign factors. Okay, but I also said that Hugenholtz diagrams are very helpful in generating the Goldstone diagrams. In other words, Hugenholtz diagrams can be viewed as an intermediate step toward producing the Goldstone diagrams. Of course, then the question emerges, well, why do we want to use Goldstone diagrams? We already know that Hugenholtz diagrams are fewer in number, so it seems like that's the most efficient form of diagrammatics. But as I said at the end of the last lecture, before the break, there are a few situations where Goldstone diagrams are extremely useful. I cannot discuss all of them in this class. There are, I would say, still too many. But one of them I would like to discuss, and that is the situation where we deal with spin-independent operators in electronic systems. Okay, and where our electronic system is a closed shell, many electron problem, say a closed shell molecule, a closed shell atom. Similar considerations could be extended to nuclei, but I would say that would not be extremely helpful because in nuclei we rarely deal with operators that have no spins in them. Okay, so that would not work very well. But in quantum chemistry, of course.
Isospin?
Yes, but there is no good calculation in nuclear physics which doesn't use a Hamiltonian that contains spin, right? So that is a problem. In chemistry, of course, we can get away with it because we have in a non-relativistic description, the Hamiltonian is a spin-free quantity, meaning that there's no spin information in it, and that means that we should be able to integrate the spin variables out. Okay, of course, you can always do it algebraically. So I could say, well, okay, do it algebraically, let's move on to the next topic, but I will not do this. I will show you a very neat procedure which allows you to integrate spins out in closed shell systems, okay, diagrammatic, with the help of Goldstone diagrams. So Goldstone diagrams are useful. So imagine that I have a situation, I have a closed shell electronic system where our Fermi vacuum, Phi, is built by simply occupying spatial orbitals with alpha and beta electrons, okay? So say if I wanted, let me start maybe with a little picture that represents this. So imagine that I have spatial functions. I'm going to use capital letters for them, as I did quite some time ago when we discussed spin-independent operators. So I1 for this one, I2 for this one, say In minus 1 and In here. So these capital I's are spatial single particle functions, which we would typically call orbitals, and I'm going to build our Fermi vacuum by simply occupying each of these orbitals with two electrons, okay? One going up and one which is an alpha electron and one which is a beta electron, okay? I can do this because I can multiply the spatial function by spin up or spin down states. So I'll have 2 here, 2 here, 2 here, and 2 here. So this is a closed shell determinant obtained by putting 2 electrons, alpha and beta electrons, on each of these orbitals. Of course, you know, little n must be capital N over 2. That is, we are assuming that we have an even number of electrons. So algebraically, this determinant is, let me try to write it here. So I have orbital 1 times spin function alpha, then orbital I2, then orbital I1 times spin function beta. That's the first pair of electrons. And then we go on, and the last one will be IN alpha, IN beta. Okay? So let's sort of write it this way. The anti-symmetrized product of these single particle states, where each one of them is either alpha or beta, of either alpha or beta type. Okay? So in a situation like this, and as I said, in chemistry this happens very often. Okay? Every closed shell molecule, okay, will have such a determinant as a starting point for the calculation. Okay? We would call this typically a restricted Hartree-Fock determinant if we produce our orbitals in restricted Hartree-Fock calculations. Okay? So if you have a situation like this, then of course it is quite natural to build our single particle basis for many body considerations, okay, by simply multiplying spatial functions by spin functions. So I already did this for occupied states, so let me sort of summarize what I did. So for the occupied ones, which we label I, I'm multiplying spatial orbital I by the corresponding spin function, which I'll call sigma, associated with orbital I, and this sigma I here is either alpha, state alpha, or state beta, okay, meaning that this is formally an eigenstate of spin operator with S squared, with the S squared eigenvalue of, with the S of 1/2 and SZ of 1/2, and this one is S 1/2 and SZ minus 1/2. We all know that, so I spend a long time on this. So that's how we build them. So actually specifically in this particular setup that I started with, if I want to know what are the spin orbitals with odd indices, you can see that they're all alpha spins. So what I'm doing here, I'm taking orbital lambda and multiply it by the spin function alpha, okay, to produce a spin orbital I2 lambda minus 1, okay? And if I want to see spin orbitals corresponding to beta electrons, those will be, according to this diagram here, the ones with even indices. So we have I lambda times beta, okay? And of course I can do the same with unoccupied states, okay? Those are orbitals in the phi, but of course we have all these orbitals above the Fermi level. Then we can do something similar for them. So we're going to be talking about unoccupied states alpha and unoccupied states beta. So for the alphas, again, let's make a convention. Let's use the convention where the alpha electrons are associated with the odd indices. So here we have a spatial function capital A times the alpha spin function, and then here we have an orbital A multiplying the beta spin function, and those will be the spin orbitals labeled with even indices. Okay. So in general, I have maybe one more. So right up. So if I have a spin orbital I, that's the product of the orbital and the corresponding spin. Then if I have a spin orbital A, that's the product of an orbital, spatial function capital A and the corresponding spin. And of course, if I will be talking about some generic spin orbitals, without telling whether they're occupied or unoccupied, in this particular setup, okay, if I have a spin orbital, say Q, then I can write it as a product of the spatial function q and the corresponding spin function sigma q. Right? In first quantization, if we went back to the beginning of this class, that would mean that psi q, a single particle state psi q, which depends on x, y, z and spin coordinates of a single electron, it would equal this some sort of a spatial function phi q, which depends on x, y, z coordinates of an electron, or you can also use the radius vector notation if you like, and then the spin function, okay, which is alpha or beta, which of course operates in a different space, in the space of spin variables. Okay? So that's the setup. So, of course, it is rather straightforward to prove that this determinant phi is an eigenstate of the total spin operator corresponding to spin equals 0. So in other words, if I consider the total spin operator, which is the sum of spin operators for individual electrons, okay, then it is straightforward to show that if you apply s squared to phi, you end up with a 0, and if you apply sz, the total sz to phi, you end up with 0 as well. Okay? For the sz, that's trivial. You have the same number of alpha spins as the number of beta spins, so they cancel out. You end up with a 0. For s squared, it's a little bit more work, but you can always relate s squared to spin raising and spin lowering operators, s plus and s minus. Okay, and they operate very trivially here. What does say s plus the s plus operator do for a single electron, right? If you have a single electron, say in the alpha spin state, then s plus will simply annihilate it, right? If it's in the beta spin, then beta becomes alpha, right? So s plus beta will give you alpha, and similarly for s minus. A very simple algebra, just a little bit of work, okay, and a few lines, and you can prove that these two are correct expressions. And that is really a manifestation of the closed shell character of our system, or of our determinant phi. Okay, so which means that if I am using now spin-independent operators, then the resulting wave functions will be singlet states, okay, s equals 0 state, okay. All right, so now let's try to do this diagrammatically. So if I wanted to do this diagrammatically with this particular basis set we're using here, each line will be labeled with two sets of indices, okay? Since we are writing these spin orbitals in this factorized form, each spin orbital is a product of the orbital part and the spin part, then each line in a diagram will have to be labeled by the orbital index and the spin index. So we'll be talking about alpha lines and the beta lines, okay? So for example, if I have a, say, whole line going this way, previously we would just put an I symbol or a J symbol or something like this added. Okay, right now, this will be a line which will have two symbols added. One for the orbital part and one for the spin part. Okay? Of course, each of these could be, this one could be multiple indices if that's what you want to do, because of course the orbital can have some quantum numbers behind it, so of course we can make it very elaborate if we want, but I'm not going to do that. Okay? If I have, say, a particle line, previously we would just stick the symbol like A or B or C, and right now we have to stick two symbols, one for the orbital part and one for the spin part, which will be alpha or beta. So now, if I want to perform some calculation, many-body calculation, where I have some determinants and I have some operators, then of course, it depends what these operators are. If they are spin-dependent, then of course, that would be a little bit more tricky, because I would have to use spin recoupling techniques, things like Usefulness diagrams and so on. But the situation greatly simplifies if operators involved are spin-free. As I said, for example, the Hamiltonian of a molecular problem in a non-relativistic description is spin-free. Or if I have, say, a dipole moment or a quadrupole moment in a molecule, those are all spin-free quantities if we talk about electric dipoles and quadruples and so on, and other operators. Okay, so let me so of course what that immediately says that spin variables are there because we need them in a Many electron system. However, we can integrate them over because essentially no operator will act on them. Okay? You can do this algebraically. That's a little bit laborious. I'll show you that you can do it very easily using diagrams. So, well, let me start maybe here. So imagine I have some, and we'll do it with Goldstone diagrams. And you will see why we need Goldstone diagrams in this case. So I'm going to sketch some resulting diagram in our calculation. Once again, using our blocks, where I will emphasize one specific Goldstone vertex. Okay? Let's assume that this vertex is a k-body vertex. With k-body means that there will be k lines leaving it and k lines coming into it. I'm not making any assumption whether the lines here are particles or holes, okay? So I will label them in a generic way, but I will label them according to this new convention where each line has two sets of indices. The indices for the orbitals and indices for the spins. Okay, so for example, this line would be, say, R1, sigma R1, meaning that this is orbital R1 and the corresponding spin at this line is sigma R1. I said it's a k-body vertex. So that means that for this line, I'm going to say Rk sigma Rk. All right? And here, for the lines that are coming in, I'm going to use this S symbols. So S1, sigma S1 for this line, and Sk, sigma Sk for this line. Now, so if I have a Goldstone diagram with this k-body vertex in it, well, let's start reading. If I want to read it, of course, one of the things you have to read, of course, signs, and weights and all these things we know how to read. We just read them as we did before using using the rules of diagrammatics. But I want to emphasize, focus on the scalars. So what is the scalar factor associated with this expression? Okay, and I'm going to focus specifically on this matrix element. So this matrix element is, you have R1, sigma R1, that's your first spin orbital in the graph. Then you will have R2, say let's write a few of them, sigma R2, and then we have Rk, sigma Rk. I'm going to put them in little brackets, okay, to emphasize different spin orbitals. So we have k spin orbitals in the bra. Then we have an operator, I'm going to call it little ok, k-body operator of some kind. Okay, and then we have indices in the ket. So S1, sigma, S1 for the first spin orbital, then S2, sigma S2 for the second spin orbital, and then Sk, sigma Sk for the spin orbital number k in the ket. Okay? And so that's the matrix element that will result from this particular vertex. Now, as I said, if OK was an operator that had spin variables in it, some sort of spin dependent, then of course there would be a harder calculation because you would have to simply apply, you would have to now take product of spins here, and then some operator that affects them, so you would have to use Piecuch-Gordon coefficients or essentially in general methods of angular momentum that can be done diagrammatically using Usefulness diagrams, but that would be a different course, okay, about them, and an interesting one too, probably. But I'm not going to do this. Let's make an assumption that OK is spin independent. Okay, well, if it's spin independent, it acts only on the capital symbols, which represent orbitals, but it doesn't act on the spins. Okay, so I can essentially factorize this expression and write it as a product. There will be an orbital part, which is R1, R2, capital symbols, R1, R2, Rk, little ok, and then capital symbols S1, S2, and then Sk, all right, times a bunch of Kronecker deltas associated with various products of spin functions, okay? If you really look at this expression, this is a spin of, say, particle 1 in our integration running into spin of this particle 1. And so I will end up with a canonical delta, sigma R1, sigma S1, okay? As you can see, I'm bypassing OK because OK doesn't act on the spin, so I don't have to worry about it. Then I'll have a similar canonical delta, which involves the inner product of sigma R2 and sigma S2, okay? We just take spin of second particle and spin of second particle here. Oh my goodness. That's what spin break does to you, right? You have to losing voice. Should be the other way around. Anyway, so we have the second delta, and then of course I put some dots, and the last one will be an inner product of sigma Rk and then sigma Sk. Okay. So you can see that in a situation like this, we have this nice factorization. There is a matrix element that contains only the orbital information, and then there's an algebraic factor that involves the various inner products with the spins. Well, if you think about it, I don't need to draw this diagram in its complexity to read this matrix element. I can drop the spin variables, and I'm going to be able to read that matrix element from the corresponding orbital diagram. Okay? So I'm going to use this language. If this is a spin orbital diagram, then of course you can see that I can obtain the information about at least the matrix element that is associated with it from the corresponding orbital diagram, which will look the same way as the spin orbital one, except that I will not have to label the lines with the spin variables. All I need to do is to take the corresponding orbital indices. So R1, Rk, S1, Sk. That's the orbital diagram. Okay, it's the original diagram stripped of the spins. Okay, this diagram certainly gives me the scalar correctly, because I read outgoing lines, incoming lines. Okay, it will give me the right sign, because for the sign, all you need to look is you count the loops and open paths, and for this you don't need to see spin variables at all, right? It will give me the weight, because to get the weight I just need to look at the skeleton. No need to worry about spins there. So essentially I can read the entire expression, except for one part. Those spin factors, right, which are obtained from the procedure of factorizing each matrix element into the orbital part and the spin part. So in other words, we can imagine right now the following. Each spin orbital diagram in our calculation will become a product of the orbital part and the spin part. So I'm going to write it right now with words. Okay, there will be some sort of spin factor, which is obtained from these kinds of inner products, also spins, of course summed over the corresponding spin variables, because each sigma could be an alpha or beta. Okay, so each of these, so you have of course some multiple summation involving the spins. But that's essentially how these diagrams will factorize. So let's look into this with with sort of more closely. Right? So let me go back here and try to do this. Okay. Well, as you know, when you look at Goldstone diagrams, and actually maybe I should emphasize, why did I need Goldstone diagrams to do this? See, I would not be able to do this factorization if I use Usefulness diagrams, because Usefulness diagrams use anti-symmetrized matrix elements. Okay? So this step, okay, that I perform here was possible only because I'm using a non-symmetric matrix element. So I can separate the spins from the orbital parts. If I use an anti-symmetrized matrix element, then I wouldn't be able to do that. So we can only do this at the level of the Goldstone diagrams. Okay? Well, anyway, returning back, if those are Goldstone diagrams, you know that there are two elements in them. Every Goldstone diagram has open paths and loops. So let's sort of now see what is the consequence of factoring out the orbital parts on the loops and on the open paths. Let me start with an open path. Again, sketching it in some way. Similar to what I did some time ago. You remember, we're drawing pictures like this. We have the rest of the diagram here. And I'm going to have a bunch of vertices, assuming that all of them are spin independent. We're talking about operators which are spin independent. So each vertex you're going to see here will be spin independent. Okay? So when this is an open path, I have some line that leaves it. There's a line that comes into it. And there are lines that are maybe, of course it depends on the path, but there may be internal lines in the path. Okay? I am not making any specific assumption whether these lines are particle lines or whole lines. Of course the picture sort of suggests the particle flow, but I'm really not making an assumption. Okay, I just have to draw it somehow. Okay, so please don't worry about the particle flow character. It's not important here at all. Okay, and let's just start labeling these lines. Of course, we have to do this first at the level of the spin orbital diagram. I draw the spin orbital diagram and I label the lines like I did here with the orbitals and spins. So I'm going to use symbols R, sigma R for this one, and S, sigma S for that one. Okay? So the line that leaves the path will be orbital R and the corresponding spin. The line that comes into it will be orbital S and line sigma S. For the internal ones, I will use Q symbols. So here, this one will be Q1 sigma Q1. Okay? The next one will be Q2 sigma Q2. Alright? This one here will be Q3 sigma Q3. So orbital Q3, spin that corresponds to it, sigma Q3. And for the last ones here in this picture, let's call this one Q omega minus 1. I'm going to assume there are omega internal lines. So Q omega minus 1, sigma Q omega minus 1. And this one, the last internal line in our picture will be Q omega sigma Q omega. Okay. Okay, that is our spin orbital diagram, or the open path in the spin orbital diagram. Well, we already know what we can do with it. If all the vertices here are spin-free, that is, they do not act on spin variables, I can separate it into the orbital part as I did before. So in other words, I can represent it by a picture which will have same set of vertices. Try to recreate it. Where I'm now dropping the spins, so R here, Q1 here, Q2 here, Q3 here, arrows, what was it, omega minus 1 here, Q omega here, and then S here. So that's the orbital part, obtained by simply summing over by extracting the spins out, okay? And now I have to sum these spins over, because I'm assuming that our spins can be alpha or beta. So what do we get? Maybe I'll emphasize. So this is now an orbital diagram, from which I can certainly read the I can read the sign and the scalar, because scalars will depend only on orbitals. So this is an orbital diagram, okay? And then let's see what is the corresponding spin part. Well, a lot of summations over spin variables. So I'm going to have a summation over sigma R and sigma S, okay? The spin that leaves and spin that comes in. Each of these summations, remember, is from -1/2 to +1/2, two values for the beta and alpha spins, okay? And then I have a summation over these other spins associated with the internal lines. So we have sigma Q1, sigma Q2 through sigma Q omega. Okay, all these spins of internal lines, and then I have to start writing our deltas. So what we have is, maybe I'll write it below, okay, not here. So our deltas are sigma, you know, when you start reading, spin of this line, okay, will be running into spin of this line. So we're going to have an inner product of spin sigma r and sigma and spin of line q1. Okay? Then I'm going to have, through this vertex, an inner product of the spin q1 and spin of line q2. Okay? Well, then there will be an extra, of course, you know, with q3, so we'll have sigma q2, say, running into q3. Okay? Sigma q2 here, sigma q3 there. Of course, then I'm going to have to put some dots. And at the end of our expression, I will have, let's just write a few last terms. Let's lay up on these dots here. We'll have sigma, what is there? Q omega minus 1, sigma q omega, okay? And then sigma q omega running into spin sigma s. Okay, that's how our expression looks like. All right, so there is an orbital component of it, which you obtain by simply removing the spin variables from, and that is good enough to read the information about, for example, scalar factors, because they do not contain spin. But then there's lots of these spin canonical deltas, right, that emerge because we still have them in our calculation. But there's one more thing, you know, that I would like to emphasize. That is the operator part. You remember, when we have an open path, we always associate the pair, x dagger, x pair of operators with each open path. X dagger for the line that leaves the path, and x for the line that comes into it. Well, in our case, this is going to be a normal product of, you know, we have x dagger r sigma r, that's the outgoing line, and then x s sigma s. And I'm going to put these dots because, of course, there may be other open paths in the calculation, okay, which I'm not looking at. So that's the general structure of our expression. Well, let's see if we can somehow simplify it. Well, one thing that you see immediately is that there is an orbital part. So I will now continue. I'm not going to read all this picture once again. I'll simply write that there is an orbital diagram part from which you can read the matrix elements directly. And then we have to perform these summations involving the spins. Well, let me remind you that spin functions alpha beta form a complete set in the spin 1/2 space. Okay, in other words, if I have an expression, say spin sigma and projection operator for spin sigma, and if I sum it over two of, you know, possible values of the spin, minus 1/2 and 1/2, or alpha and beta, then of course that produces the identity operator in the spin 1/2 space. Okay? And we are in that space because we're talking about electrons here. So we end up with an so I'm going to actually use this information. Maybe I'll use my color to emphasize what I'm going to be doing. It's right here. You can see that what I have all these summations of our spins of internal lines. You know, there is this one here. You have to sum it over Q1. Okay? Well, that will give you a unit operator. Then I have to take this part here, maybe a different color. Okay? If you sum this over sigma Q2, it will also give you a unit operator. You see, and I can continue in this way, all the way to the very end. Okay? Summation over CQ omega, sigma Q omega here. Okay, will give you also the unit operator. So in other words, all those intermediate spins will, when you sum them over, will give you the unit operator, and you just end up with the initial spin and the final spin, or I should say the other way around, I guess. Initial spin and the final spin, okay, of our open path. So if I continue now this calculation, what I will have is this. I will have an orbital diagram times the summation over sigma r and sigma s. And then we'll have an inner product of sigma r. You see, I can now ignore all these things in the middle, and I have sigma r inner product with sigma s. Okay? And then I will have a normal product of x dagger r sigma r x s sigma s. But you have to remember that, okay, but we have here this is canonical delta, okay? Meaning that I can shrink this summation to a single summation. So I'm going to have here an orbital diagram, that is the algebraic expression obtained from reading the orbital diagram, times the summation over single spin variable. I don't have to call it sigma r or sigma s, I'll just call it sigma, because I'm dropping just to 1. Going from -1/2 to +1/2, okay? And I have a normal product of x dagger r sigma x s sigma. So you see, what's left over is much simpler than compared to our starting point. You know, we started with the spin orbital diagram with lots of orbital and spin information in it. We end up with an orbital diagram obtained by simply dropping the spin variables completely from our picture. And then what is left of the open path is just this, essentially, right? Everything else I read from the orbital diagram using spatial orbitals that are associated with the lines. You remember what we had before here? Before we had x dagger x only, a single pair. Now we have a sum of these two pairs. If you really write it explicitly, it's actually worth doing. It's going to be x dagger r alpha x s alpha. So there is an alpha component of this expression, and then there is a beta component of this expression. Okay, because you have to sum over two projections of the spin here. -1/2 and +1/2. Okay? Do you remember what this expression was? You still remember? It was a long time ago, but what this represented? We talked about it in one of the classes when we talked about spin-independent operators. Okay, that's fine. That's fine. It was some time ago. You remember we introduced the symbols ERS for such quantities, and I call them the unitary group generators. Okay, or generators of the unitary group, or the algebra, right, associated with the unitary group. Okay, so this is what you get. So you see, what you're learning is that when your operators are spin free, then a diagram becomes an orbital diagram times for each open path, we end up with a unitary group generator associated with the lines of that path, of the external lines of that path. Okay? Well, all right. So we'll remember that. You see the benefit already. You always have to see where the benefits are. The benefits are enormous computationally, because if I use spin orbitals, there are twice as many spin orbitals in the basis as the number of orbitals, because each orbital can be alpha or beta. Okay? So when I read our expression, the summations over the orbitals will be much shorter. Twice as short. And if you have one of them, well, that's just a factor of 2 saving. But if you have many of them, well, that's a huge factor. Okay? If you write a computer program based on spin orbitals, it's going to be much slower compared to the program written based on orbitals. So it's worth doing, because your savings will be 2 to some power, right, of the number of vertices you have in the diagram. Okay, well, let's look at the consequences of the presence of the consequences of using orbital diagrams on the loops. Okay, so maybe I'll do it here. And then you will see a sort of one of those very interesting things about diagrammatic. So, what is a typical loop? Well, again, I'm going to sketch it the same way I did before. We'll have a bunch of vertices in a loop. Maybe I'll just emphasize those 4. Okay, we have to connect them, lines. Okay, and then of course we have to close the loop. Okay, well, that's a loop. Again, I'm not suggesting any particle whole character right now. It's irrelevant for these considerations, okay? So let's label the line. So this is going to be R sigma R, if I start with a spin orbital diagram, okay? Well, this one here, I'll follow the previous notation. So it's going to be, say, Q1 sigma Q1 for this one, okay? That internal line. The next one will be Q2 sigma Q2. So the orbital Q2 spin associated with it. Then this one will be Q omega minus 1 sigma Q. I don't like this line. You don't have to do anything else. Bigger. More space. So Q omega minus 1 sigma Q omega minus 1. And then this one will be Q omega sigma Q omega. Okay? So that is a spin orbital. That's a loop that we're looking at in a spin orbital representation. Once again, just like we did before for the open path, or initially for the resulting diagram, I can drop the spins out because each of these vertices is spin free. Okay? So I end up with a very similar picture. Okay? Except that I will not use spin labels. Let's do it one more time. So I'm dropping now the spin variables. So we have Q1 here, Q2, Q3, sorry, Q omega minus 1, and then Q omega. So we have Q1, Q2, Q omega minus 1, Q omega R. So that's the orbital part. So we can read from it all the scalars, you know, all the matrix elements, obviously. But then we have to look at what is the spin doing here. What are the spin variables doing here? So we end up with, again, a summation over all the spin variables. We have a summation over sigma R, and we have a summation over all these intermediate spins. Sigma Q1 through sigma Q omega. Okay? And once again, I just have to write the corresponding canonical deltas. For the first vertex, I have an inner product of sigma R, spin of line R, and sigma Q1. Okay? That's this one. Then next one will be sigma Q1 running into sigma Q2. So inner product of these two spins. Then you continue, and if you look at the last terms, we'll have sigma Q omega minus 1. That's this one here, running into sigma Q omega. And the very last is an inner product of sigma Q omega with sigma R, closing the loop. Okay. And once again, let's sort of try to analyze this. Again, we can use the resolution of identity. Okay? Summation over sigma Q1, okay, here will give me the unit operator. Summation over sigma Q2 will give me also the unit operator. Summation finally over sigma Q omega will give me the unit operator. So essentially, all these intermediate spins will sum over to the unit operators. And I'll be just left with the following. I'll be left with the orbital diagram. So again, I will not redraw it, I'll just write it in plain English. So end up with an orbital diagram times the factor that comes from the spin consideration. So what do we get there? We have a summation over sigma R that, let me remind you, goes from minus 1/2 to plus 1/2, because we're talking about electrons and alpha, beta spins in them, okay? And then we have sigma R, then all these intermediate spins are gone, okay? And we run into sigma R because we're closing the loop, okay? But inner product of sigma R with itself is 1. Spin functions are normalized to unity, so this is 1. We are summing a factor of 1 twice because we have two terms in this summation. So then it's just 2. Okay? So I end up with an orbital diagram, or orbital, the loop of this orbital diagram times a factor of 2. Okay? Because as I said, this thing here is 2. You can actually see that if, what is 2? It's a multiplicity, right? For 1/2. Okay? If I had some other fermion, say with an angular momentum, say J, and if my operators were spin independent, that is not acting on the J variables at all, then I would end up with 2J plus 1 for each loop. Okay? I'm not going to do this because I don't think there are too many situations in nature that really do this, because once you have fermions with higher J values, typically your operators become spin dependent, so it would not be extremely useful. But I guess you can see the rule that is emerging out of it, and that's what I want to emphasize. So we end up with a factor of 2 per each loop. Well, look, so that means that we have now a fantastic way of doing the diagrammatics in the case of, say, closed shell electronic systems. Okay? Start with a Fermi vacuum, which is a closed shell determinant, where you occupy each orbital twice with alpha and beta electrons. Okay? And then draw the resulting diagrams, Goldstone diagrams. Now you can go through Huggins. Remember, that is just an algorithm. You can start with Huggins, non-oriented vertices, then go to oriented ones, then then do line exchanges, and you end up with Goldstones. Okay? Spin orbital Goldstones. What do you do with them? If you want to know the orbital expressions, you replace spin orbital indices by orbital indices, the spatial orbital indices, and then you do the following. With each open path, you associate this factor, the unitary generator, unitary group generator, okay? That is the x dagger x pair summed over the spins. And with each loop, you associate the factor of 2. So altogether, your diagram will end up with a factor of 2 to the L, where L is the number of loops. Okay? And you can see all this spin integration work diagrammatically. Okay? So let me illustrate this. I guess let's have a little break and I'll illustrate this with one example, and then we'll move on to the next topic, the independent parametric approximations. Do you have any question about this analysis? Anything that you feel needs? Okay? As I said, as I presented it, it has limited use mostly to quantum chemistry or to electronic systems, okay, in general, where you have closed shells. All right? And of course, there's already a lot of use, so it's good to know it. But you can see also that there is a certain thought in it, deeper than what I presented. That is, Goldstone diagrams are very useful because when you use non-symmetric matrix elements, you can always propagate the spin through the open path or through the loop. Okay? So even, here I made an attempt to integrate spins over because I was assuming that our spin variables are free, so I just sum them over. And I ended with a factor of 2 per each loop, for example. Right? Just summing these spins over. But even if I didn't sum over, suppose I didn't want to do that. Right? Suppose I wanted to talk about the approximation, which in quantum chemistry is described as different orbitals for different spins. In other words, suppose I would make an assumption, as we often do in the unrestricted Hartree-Fock calculations, for example, right, where orbitals associated with the alpha spins are different than orbitals associated with the beta spins. Okay, so interspin polarization. It's a mathematical technique. You don't have to do this, but you can, to lower the energy further, quite often. Right? Well, then of course I wouldn't be able to do what I did. I wouldn't be just dropping spins in some sort of naive way, because each line, say corresponding to spin alpha, would also have an orbital, which would have to be labeled with an alpha. I mean, they would have different orbitals for different spins. However, I would still be able to propagate spin through the loop. Okay, so in other words, or the open path. If I started with alpha here, well, that will be alpha all the way. Okay, and if I started with beta, I will be going with beta all the way. Okay, so even in calculations where we cannot integrate, which are not closed shell situations, in general, maybe I should say, open shell situations, right? The Goldstone diagrams are extremely useful. So when we write, for example, in quantum chemistry, open shell couple clusters, say, or NDPT or some other codes like this, right? Then what you do is you still use Goldstone diagrams. because then you can integrate over the spins along the loops and along the open paths, because they sort of propagate through the use of non-symmetric matrix elements. Okay, and you gain a lot of efficiency, because you always have to remember the number of orbitals, the spatial functions, is twice as little as the number of spin orbital functions. Okay, so you save a lot of time by doing such a thing. Okay, so there's a lot more to Goldstone diagrams than meets the eye, and of course there are all kinds of interesting cancellations of diagrams and all things of that sort, right, which happen only when you start doing Goldstone diagrammatics, right? You know, Goldstone diagrams are extremely compact. There are few of them, okay, and certainly if you want to quickly derive the spin orbital expressions, that's the best way, okay. But you know, there is still sometimes a need to expand each of these Hilton vertices and see what's in it, because the exchange contributions and the sort of these Coulomb type contributions may have different magnitudes, right? And you may want to play sometimes with this information. Okay, so there's lots of interesting stuff about Goldstone diagrammatics. But here I give you one example, and I'll show you after the little break what can be done with it and how things simple. Okay, so let's have 5 minutes. So, how was your weekend?
That's okay.
So I flew over the weekend with my daughter to New York to see the Broadway show, which she really wanted to see.
Oh, yeah?
So that's crazy a little bit, right? But everything went okay.
What show?
This was The Crucible. Lots of famous actors there. It's amazing the number of theaters they have there. It's like, it's probably the largest concentration of theaters anywhere in the world. It's about 50 theaters. In just the Broadway, proper Broadway. I'm not talking about the rest of the city. Amazing.
Forges lenders at mass climates. We're gonna be able to plus 500. It's gonna be damn. That's all it does.
Keep the flag operator.
It's interesting how these spring breaks line up, right? So, and MSU, they had one 2 weeks ago. My daughter has it now, this week, and we had it, so we had, last week, right? So we had 3 weeks of spring breaks in different universities. Very hard to organize family life, actually. You want to go somewhere, right? You can't do it. I wish we had some sort of computer centralizing this. This part. No more, this part, yeah. Okay.
Well, if all the spring breaks were at the same time, Florida would be overrun, right?
Yeah, I guess that's the problem. That's a hidden agenda.
It's the hotel owners that run the whole system.
Well, or, but many people, after a few years of trying, noticing that you can't get a spot in the hotel anymore, right? They'll start using other parts of the country. Discover how beautiful it is. It's not just Florida. Nothing against Florida.
What is that you're talking about?
Okay. Okay. I guess, is it okay if I start over? Okay. So, so with these ideas that we discussed, let's have one example that shows you, I will show you how these things work. It's going to be a very simple example. I will try to determine the expectation value of the V operator, okay, in the Fermi vacuum state phi, where phi is a closed shell determinant, okay? So let's start, first let's sort of summarize what is that we would do if we wanted to do this using spin orbitals. Well then, let me actually run quickly through the procedure. You start with, we have one V vertex, okay, we have to form the lines with, the diagrams with no external lines. So then, if I start with the non-oriented Hugenholz vertex, that's what it would be, okay? So this would be Hugenholz skeleton, non-oriented. Then the next step it would be to, you would add lines. So you would add the arrows, so we would end up with the Hugenholz oriented skeleton. And the next step would be to introduce some indices. I guess we know that lines that are associated. Okay. Let's continue on the same footing. Lines that are emerge from the same vertex are always holes, so I have to use symbols I and J here. Okay, so this would be Hugenholz diagram. And of course, if I wanted to use the Hugenholz diagrammatics, my next step would have to be to draw the Brando. Okay? Okay, Brando. And you could evaluate the expression from it. Or we could continue to Goldstones by doing line exchanges. So Goldstones would be this and this. Right? So I, J, I, J. Okay? So you would use a single Brando or two Goldstone diagrams to produce the final expression. Okay? And if we want to read this, you can see that, let's use the Goldstones. So the weight of each of these Goldstones is 1/2. And the sign factors For the first one, the sign factor is -1 with 2 loops and 2 internal whole lines, so it's a plus. And for the second one, the sign is -1 to 1 loop plus 2 internal whole lines, so that is -1. Okay? So the final expression then, using spin orbitals, would be as follows. It would be 1/2 sum over ij would have ij v ij for the first Goldstone diagram, outgoing lines ij, incoming lines ij in the same order, and then from the second diagram, outgoing lines, if outgoing lines are ij, then the corresponding incoming lines are ji, right? Because j comes into I and I comes into j, right? I already did this, so this is just a reminder, okay? Which of course you could also write in a compact form as 1/2 sum over ij, ij, v, ij, anti-symmetrized, okay? So that's the well-known formula for the expectation value of the v operator. And of course you could also obtain this expression from Randall, okay? Weight of this Hugenholz, you know, if you wanted to do it at the Randall level, you'd look at the weight here. Weight of the Hugenholz is 1/2 because we have 2 equivalent Fermion lines, okay? Sign of the Brandau is plus, and then you would read it directly as this. So either way, we will obtain the same result, okay? But I did it mostly from the Goldstone diagrams. Okay. Well, let's see how this now. Suppose I want to now integrate the spins over, okay? Using our trick with at the level of the Goldstones. So let's look at. We have to start with drawing orbital diagrams. Oh, they must be Goldstone diagrams. Okay. So we'll have, essentially you take the spin orbital diagrams, okay, as you see them there. But instead of using lowercase symbols ij, I'll use capital case symbols ij because I'm talking about orbitals now. So capital I, capital J are orbitals, spatial orbitals. Okay? Those are orbital diagrams. Then, the next thing that I have to do is to read them. So, the weight here is 1/2. Weight here is also 1/2. We talked about it before. Signs are the same as before. You know, these things don't depend on spin orbital versus orbital representations. So here sign is +1. We have 2 loops, 2 internal whole lines. Here is -1. 1 loop, 2 internal whole lines. Okay, so what is then the expression? Following our rules. For the first diagram, I get 1/2, a summation over capital I, capital J. Those are summations over orbitals. Okay. Matrix element is outgoing lines are ij, incoming lines are ij in the same order. So it's going to be ij, v, ij. Okay. That matrix element is, of course, you know, normally if you wanted to compute it, would be an integral of orbitals. Pi r1 star pj. Can squeeze it there? But as a reminder, maybe once in a while we can do these things. Okay, so this one here would be an integral of phi star r1 pj r2 times v, which acts, this is now spin free, so it acts only on xyz coordinates of 2 electrons, and then we have phi r1, phi j r2, and you integrate over r1 and r2. Okay? Not over our symbols x that we use for spin orbital representation. So those are just, this is now a 6-dimensional integral, okay, that you have to calculate. All right? And then the second part of our expression will be, you know, normal would be -1/2 sum over ij, v, ji, okay? But I am missing still one thing, right? You know, remember, we have this additional rule now, that we have to associate a factor of 2 with each loop. We don't have open paths here, so I don't have to worry about that. But we have to associate a factor 2 to the L when we have L loops? Well, here we have 2 loops. So you have to stick the factor of 2 squared in front of this expression, because we have 2 loops. Here we have 1 loop, so you have to stick a factor of 2 to the 1, meaning 2. Okay? For this one. That's how you read these diagrams. You read them with this extra rule of 2 to the L for the loops. Okay? So let's see what we get then. Well then, phi, v, phi becomes, you have 1/2 times 2 squared, that's going to be 2. And here we have 1/2 times 2, that's going to be 1. Okay? And we have a summation over ij in both cases, so I can recombine this, and we end up with a summation over ij. Okay, we have 2 ij b ij minus ij v ji. In other words, if you use the language of Coulomb and exchange integrals, I have 2 times Coulomb minus 1 exchange. Well, that's what happens for a total cell. You know this problem because you must have seen it in various applications earlier in your life. Okay, but that's how we get it diagrammatically. Okay, and let's actually see. Of course, I sort of spend time talking about it, but you can see how quick that goes. I just use the rule 2 to the L, and that's all I do. Okay, a very simple calculation. Now, what if I wanted to do this algebraically? Okay, it looks like a simple case. So I'm going to perform a procedure, I'll call it here verification. Okay, using the algebraic approach. And you will see how much more complicated that would have to be, even in such a trivial case. So algebraically, I would have to start with this expression. Not this one, because here I cannot integrate spins over. I can integrate spins when I use non-symmetric matrix elements. Okay, so I will get phi v phi equals 1/2 sum over little I little j ij v ij minus ij v ji. Okay, now if I want to integrate the spins, I have to realize that I is capital I times the spin of it, and j is the capital J and the spin of it. So I have to replace this by the following. We have 1/2, we have a summation over spatial orbitals ij, we have a summation over the corresponding spins sigma I and sigma j that run from minus 1/2 to plus 1/2. So we have 2 projections of the spin, okay? And then from the first term, I would have an integral or a matrix element I, sigma I, j, sigma j, v, and then I, sigma I, and then j, sigma j. Right? That would be the substitute for this matrix element, ij, ij. For the other one, I would end up with I, sigma I, j, sigma j, then v, and then j, sigma j, and then I, sigma I. Okay? And then we will close the round bracket and the curly. Okay? That's how we would have to start. Okay? Well, now we have to continue and perform and simplify this expression algebraically. So what do we get? We get 1/2. Okay, let's focus on the first term. So I'm gonna start with a summation over ij. All right, and in the first term, when you read it, you can see we have here spin sigma I running into spin sigma I and spin sigma j running into spin sigma j. So I end up with a matrix element ij v ij, and then I have a summation of a spins sigma I and sigma j running from minus 1/2 to plus 1/2, and what we have there is sigma I inner product with sigma I times sigma j inner product with sigma j. Okay, that's how the first term will look like, so the Coulomb part. And for the other part, okay, we have minus, and we'll have, see if I can do something about that. Yeah, that's okay. So I guess, yeah, let's do this. Here. So we have summation over ij, once again. We'll have a matrix element I, J, V, J, I, when I get rid of the spins, okay? And then I will have spin sigma I running into sigma J and sigma J running into sigma I, okay? So we end up with a summation over sigma I, sigma J, going from minus 1/2 to plus 1/2, and our canonical deltas are sigma I, sigma J, and then sigma J back to sigma I, okay? That's what we would have to do. Now let's look at these individual terms. So sigma I, inner product of sigma I is 1. This is also 1. So altogether this is 1. We're summing 1 4 times. Because we have double summation of the sigmas, yeah? There are 4 elements in it. So altogether the first part will give me a factor of, this one here, will give me a factor of 4. Okay? So we end up with 1/2 times 4 times the summation over ij, Vij. Okay? And the second term, I have here sigma I, sigma j, sigma j, sigma I. You know, the middle part, when you sum it over sigma j, will give you 1, the unit operator. And then you end up with sigma I running into sigma I, summed over 2 values of sigma I. That's going to be 2. So this part here gives you a factor of 2. Okay? All that's here is simply 2. So we end up with minus. There was 1/2 in front, so it's going to be 1/2 times 2 times the summation over ij, v, ji. And of course, you know, 4 over 2 gives you 2. 2 cancels here with that 1/2, and we end up with the right result. Okay? 2 times the Coulomb part minus the exchange part. So I got it right, but you see, it takes a longer effort already in this very primitive calculation. Imagine that this calculation had multiple v's and some other operators in them, right? And I would have to do this. So diagrammatic is much easier because all you need to do is to count the loops, right? And simply associate the factor of 2 with each loop. And for the open paths, you know, use the x dagger and x pairs summed over the spins. Okay, a very simple rule, and no need to spend a lot of time on it. Okay, so right now, I think I'm done with all these general diagrammatic considerations. We're going to now start talking about various physical theories. Okay, and the first topic I would like to focus on are the independent particle model approximations. Independent particle model approximations. We're going to use an acronym IPM for independent particle model. Okay? I don't know how many times, but if I do this, that's what it will mean. IPM will mean independent particle model. You remember when we started with the whole particle formalism, and when I introduced the concept of the Fermi vacuum, I said that it often happens, not always, but it often happens that when I write the CI representation of the wave function, that one determinant dominates it. Okay? And that's typically the determinant we choose as the Fermi vacuum. So then we have a Fermi vacuum determinant, and we generate the remaining determinants by performing particle Hall excitations. Okay? Well, if one determinant is a dominant determinant, well then, you know, it is of course reasonable to try to produce or consider approximations where we simply approximate the many-particle state by a single stated determinant. Of course, you want to make sure that this determinant is as best as you can make it. So you don't want to just guess your orbitals in some naive way. Okay, but you want to optimize them. That is, find some criterion that tells you, well, that's the best single determinant I can get. That would give me a reasonable approximation to the many particle, the correlated state. Okay? All those kinds of approximations that are based on the idea of replacing the many determinantal wave functions by a single determinant, okay, are called the independent particle model approximations. The reason we call them independent particle model approximations is that it's easy to prove. We're going to do this in MBPT, okay, that a single determinant is an eigenstate of a one-body operator. Okay? Where you're summing over one-body terms, where such that your spin orbitals in the determinant are simple eigenstates of those one-body individual terms. Okay? That's a trivial thing. So that's why we say independent particle model. That is, in single determinant is an eigenstate of a one-body Hamiltonian of some kind, okay, meaning no interactions in it. At least not real interactions. Maybe some effective interactions buried in these one-body operators. So, yeah, but not the real interactions. Okay. Now, and of course, those are behind all kinds of mean field theories as we describe them. Okay. Theories such as Hartley-Fock theory, theories such as Bracknell theory that I'll discuss here, which leads to the concept of Bracknell orbitals, and other theories. Of course, there's also a vast area of physics and chemistry, right, where we talk about density functional theory. You also use a single determinant there. It's a constant determinant, okay, which corresponds to a non-interacting system. But that is a different kind of a situation. It's not a wave function now. It's not, constant determinant is not an attempt to approximate the wave function. It's an attempt to produce a determinant that gives you an exact density. Okay, well, that's an entirely different proposition. We're not going to talk about this. There will be, of course, an interesting another class, right? But we don't have really that much flexibility in this smart sense. Okay, so we'll focus here on determinants as wave functions rather than determinants being model states to represent, say, densities and so on and so forth. Okay, so, and I will focus on two of them. I already mentioned them, Hartley-Fock and Bracknell. Hartley-Fock is a theory where you simply are trying to optimize your determinant such that you minimize the energy expression with it. Okay, so in other words, you're trying to find a determinant which produces the lowest possible energy, okay, in a variational sense. Okay, so you minimize the expectation value of the Hamiltonian with a single determinant, and you're trying to get the best orbitals that will give you the lowest possible value. Okay, and within that category, of course, we have a variety. We have restricted Hartley-Fock theories, unrestricted Hartley-Fock theories, all kinds of other solutions where you use broken symmetry solutions and so on. Okay, so there's a lot of science behind that. Okay, well, there's an alternative approach which we will talk about here, namely the concept of Bracknell orbitals. That's a concept where you're trying to optimize your orbitals by maximizing the overlap of a determinant with an exact state. Okay, when you talk about that, in a way, you could think that that's a better definition because if your determinant can be as close as possible in a sense of inner product with an exact wave function, well, that must be a pretty good determinant. Okay, of course, that immediately raises the eyebrows and say, well, wait a minute, I don't have a full exact state usually. So how would I find that kind of determinant? Well, first we'll talk about the properties of such determinants, but then there is actually a possibility to implement the practice because you can replace the word exact state by, for example, a kappa cluster state. Kappa cluster wave functions are very good approximations to exact wave functions, so you can optimize your orbitals such that the single determinant you're using maximizes the overlap with the kappa cluster wave function, which is now something you can calculate. Okay? And we have nowadays theories like Bracknell kappa cluster with doubles implemented and things of that sort. Okay, these things exist. People put the symbol B in front of kappa cluster, right? So there is of course a use for it. But I will talk about Bracknell orbitals because there are some interesting things about them in terms of theory. Okay, that I need in many body perturbation theory. Okay, so this will be my main use. And the way we'll accomplish this is, I'm assuming that all of you have seen derivation of Algebraic equations, one way or another, right? Because it's a sort of an undergraduate knowledge. However, here you will see, hopefully, a different derivation, which will be a diagrammatic derivation. You'll see the Hartley-Fock determinants can be derived, Hartley-Fock equations can be derived by drawing one diagram. Okay, so it's going to be very quick, all right, and elegant. And the same with Bracknell. But I also want to use this opportunity to derive this equation using a beautiful theorem, which is called the Thouless theorem. Okay? Why do I, so we'll do two things about this theorem. This theorem will be used here to derive Hartree equations, okay, and Bragg or the constant Bragg orbitals and so on, okay. But we will also need Thouless theorem because it is useful to understand various features of Kappa-Cluster theory. So, what is Thouless theorem? Thouless theorem says the following: if I have two slated determinants, phi and say phi tilde, such that the overlap between them is non-zero. So if you form an inner product of phi and phi tilde, you do not get a zero. Then you can prove, and that's what we'll do, that say the determinant phi tilde is proportional to an exponential operator where you exponentiate a one-body particle Hall excitation operator. Okay? When you apply such an operator to phi. Okay? So here, C1 is a particle Hall single excitation operator. One particle Hall excitation operator. Okay? In this notation, I is occupied in phi, A is unoccupied in phi, and C's are some coefficients that depend, of course, on what phi tilde is. And we'll actually see the details of it when we start deriving. It's a beautiful theorem. It tells you that if you have two determinants that have a non-zero overlap, then they differ by this sort of transformation, which is an exponent of a one-body particle Hall excitation operator. Okay? It's a general statement. So if someone tells you, I want to relate unrestricted Hartree-Fock to restricted Hartree-Fock, well, unrestricted Hartree-Fock is e to some one-body operator acting on the restricted Hartree-Fock. You know it right away. You want to say, what's the difference between Hartree-Fock and Kohn-Sham? Kohn-Sham determinant equals e to some one-body times Hartree-Fock, right? Because, of course, they will have some non-zero overlap. Okay? So, why is that useful for Kappa-Cluster? It is useful, as I said, it's going to be very useful for us when we start deriving Hartree-Fock equations. But it's also useful in Kappa-Cluster theory because you already know that in Kappa-Cluster theory we represent, at least in the single reference Kappa-Cluster theory, we represent many-body wave functions, okay, by applying, so the ground state wave function Kappa-Cluster theory is e to the t1 plus t2 plus and so on, acting on some slated determinant phi, could be a Hartree-Fock determinant, for example. And this T is the cluster operator, which is a particle Hall excitation operator, and it has the one-body part in it, typically. Okay? And it has more, of course. But because it has this one-body part, we have sort of Thouless theorem built into the theory. There is e to, because in fact, if you think about it, e to the T1 acting on the phi is essentially telling you, optimize my orbitals somehow. Okay? Rotate them to a better form. Okay, that actually explains why Kappa-Cluster results of Kappa-Cluster calculations are often numerically invariant with respect to rotations of orbitals that produce different kinds of determinants. This is actually very unique to Kappa-Cluster theory and to an exponential ansatz because in CI that would never happen. CI does not have an exponent, so it doesn't have Thouless theorem built in it. So CI calculations, results of CI or shell model calculations, strongly depend on how you choose your orbitals. Okay? In Kappa-Cluster theory, you can be quite often you can be pretty inaccurate about it. Yeah? You can sort of choose various types of orbitals and you still end up with the same final result. Because as long as you have T1 in your calculation. So Thouless theorem allows us to understand it as well. Okay? So we'll talk about Thouless theorem. Now, I don't think I can do a whole lot today. So let me just say at least how we're going to set it up. And then we'll start deriving things next time. So, of course, you have to ask yourself the question, how do I produce two different determinants with non-zero overlap? Okay? So suppose I use a notation where phi is the determinant which is produced by spin orbitals 1, 2 through n. Okay? And the associated single particle basis is going to be, if I want to write a generic member of that spin orbital basis, I'm going to call it p. okay? And I pick up simply the first 10, sorry, the first n of them I'll use to define my determinant phi, okay? And then, so those will be my I symbols occupied in the phi, and for the remaining ones, n plus 1 and higher, if I have an infinite base set, of course that goes to infinity, okay? Then those will be the ones that are unoccupied. So that's phi. Well, then the question is, what is phi tilde? If I want to write an arbitrary determinant which has a non-zero overlap with the phi, see, I cannot just pick up some other indices. Okay, I cannot just be naive about it and say, oh, I'm going to just choose some other spin orbitals, not the first n, but some other ones. Because if I choose the other ones, they will produce excited determinants, which are orthogonal to phi. Okay, so that's not going to be non-zero overlap. Those will be some excited determinants because our basis sets are orthonormal. So the only thing I can do then to produce another determinant which has a non-zero overlap is to rotate orbitals. I have to switch from this basis to some other basis, which I will call P tilde, okay, which will have its own occupied I tildes and unoccupied, okay, and then my phi tilde will be simply a determinant spanned by these tilted spin orbitals, okay, obtained through rotation from the p's to the p tildes. Okay, rotation mathematically means that you represent each of member of the new basis set, the tilted one, as a linear combination of the original ones. Okay, you sum over p and you will have p tilde p, where each of these d's, okay, must be an inner product of p and p tilde. Okay, in other words, this is what you do in algebra when I switch the basis set, right? I go from the old basis, the old one, old meaning old, not that old, right, is the one that leads to this determinant, okay, and then the new one is that leads to another determinant, phi tilde, okay, and of course these two basis sets are related because I can always represent basis set of tilted spin orbitals as a linear combinations of the original ones, okay, where the d coefficients are simply a unitary transformation that allows you to go from the old basis set to the new one. Unitary because we have to preserve the norm and orthogonality. Okay? We are talking about orthonormal basis sets. Okay? That's going to be the beginning. So of course that means that I will write this as a product of x dagger i's acting on the vacuum. You can imagine how this will start. That's going to be the first equation I'm going to write next probably. On Wednesday. And this will be a product of some tilted dagger operators corresponding to the tilted basis set. Okay? Choosing the first n members of it. And our initial equation, okay, that's for Wednesday, will be, the first thing I'll have to do is to relate x dagger tilde with x, okay? Relate them somehow. When I find the relationship, I'll be able to start computing. I'll be able to say, what is phi tilde in relationship to the phi? Okay? And as we'll continue, for say about an hour, we'll see the emergence of Thouless theorem. It might be one of the most beautiful theorems there is. Okay? It's such a cool thing that you can, you always think, what are these state determinants? And it looks like something you can't relate to each other. Well, there is a clear relationship. Determinants differ only by single excitations. What is this telling us? Single excitations are really not correlation. So you always have to now realize there's a physical consequence. If I can relate two different state determinants by e to the one body operator, or single excitation operator, it means that single excitations do not really produce correlation effects. Okay? Correlation effects are produced by double excitations or higher. Okay? And that is what you see in MBPT, that's what you see in capital field. That's why, if you want to go beyond mean field, you have to use two particle to whole or double excitations or higher. Okay? Because one body excitations only rotate orbitals. You go from one determinant to another, but you're not doing anything else. You're not introducing correlation effects explicitly. Okay? So that's going to be something we're going to be relying on. Guys, we have to stop now. Thank you very much. If you have any questions, you know how to find me, and I'll see you on Wednesday. And we have homework right at the end of this week.